Hi, everybody. My name is Ali Trollier, and I am with ECO2, which is Eco-Oxygen Technology. Today, we're going to be presenting a number 4 in our series of webcast sessions, and today's topic is sustainability in wastewater collection systems. Now, sustainability is in the spotlight, specifically with climate change and a focus on infrastructure deterioration. And today, we're going to focus on wastewater collection systems and what we can do to not only stop odors, but also prevent corrosion and protect infrastructure, reduce total cost of operation, and reduce greenhouse gases. So the agenda for today is going to talk about how to understand what is sustainability and specifically how it relates to wastewater collections. Really, this is going to be a tale of two gases, hydrogen sulfide and methane. And if you treat for hydrogen sulfide using the correct methods, you can also get credit for reducing methane formation. And we're going to show you a little bit on how to do that with some support materials from WEF Envision and a WEF group led by Brown and Caldwell. I'm going to give you some example calculations, go over a case study, and then we'll wrap up. It should be about 20 minutes. So the first thing I'd like to show is a support material that's been brought to us by WEF. And this is a document or a task force called Envision. And I've got an image of a fact sheet up here on the screen. And this is something that you can download from our website or through WEF. And what Envision is a partnership with the Institute for Sustainable Infrastructure, or ISI. So WEF partnered with ISI to form this Envision task force. And what they've done is put together a guide for projects for specifically optimizing resiliency and sustainability as it relates to water infrastructure projects. And just some different topics that they handle are like a framework for projects, evaluation, certification. There's also public recognition that goes along with these different sustainability objectives, and also awards that can be received. So Envision has put forth these 5 categories for sustainability and resiliency, and you can see them listed here. But what these categories are indicators to recognize forward-thinking objectives and projects at your different public works locations. So some different projects that you may think of when we talk about sustainability, maybe energy efficient filter upgrades or different process optimization like blower optimization or different pumping schedules. But specifically today, we're going to talk about greenhouse gases and how to reduce them in wastewater. Now, when we talk about greenhouse gases, and it's going to be abbreviated GHG here throughout, I've got a pie chart that shows what the makeup of those greenhouse gases are in our atmosphere here on Earth. And so you can see that the majority of greenhouse gases are carbon dioxide, 82% of them. But methane composes about 9% of the volume of greenhouse gas. Now, methane is actually 30 times more harmful to the environment than carbon dioxide. Now, a little diagram next to that shows just kind of a recap on how these greenhouse gases are harmful to the Earth. And what happens is that these greenhouse gases form and accumulate in our atmosphere, and they do not let the infrared light out to cool the Earth. They're holding too much of that infrared light down, and they cannot pass up through those gases. So that's what causes the global warming and the extreme climate changes that we're seeing. Now I'm going to get into a little bit of the research that was brought to us by WEF and the Water Research Foundation and these folks that are shown here on the screen. We've got John Willis, the PhD and PE at Brown and Caldwell, and these other really intelligent folks from the world of academia. And they presented their findings at a webinar for WEF in 2018. And so I'm going to present some of their findings and then give you some calculations and estimates based on their findings. So historically, sewer pipeline methane has not been considered to be a major contribution to greenhouse gases. And that is because it's relatively insignificant as far as the global or the national scale. And this chart that was developed by John Willis here, it shows a little bit about what the total greenhouse emissions are in terms of volume of CO2. And we've got some different categories for wastewater treatment, centralized wastewater treatment, and then down here at the bottom shows the methane that comes out of our wastewater sewer systems. And you can see it's a very small fraction. It's only 0.015% of all greenhouse gases. But if you think about the major contributors like livestock, fossil fuel burning for power generation, transportation and industry, these are things that we maybe don't have any control over. But what we do is we treat for hydrogen sulfide, we treat the wastewater and the sewer pipelines coming in. And so all sectors must be engaged in this fight for sustainability. And even what may be relatively smaller contributions on a national scale can still have a very large implication on a local scale. And so we're going to get into a little bit more on how to estimate what methane formation is happening in your sewer systems. So when we take a look at what's happening in the sewer pipeline, really we've got hydrogen sulfide and methane being formed under the same conditions. Now, when the sewer has no dissolved oxygen content and it has no nitrate content, this is an anaerobic condition. So anaerobic bacteria like sulfur reducing bacteria and methane formers are allowed to thrive in these anaerobic conditions. So when we've got in this diagram below, you can see sediments do not normally contribute very much methane, neither does the bulk flow. However, having anaerobic bulk flow encourages anaerobic biofilm. So this biofilm, the thicker it is, the more anaerobic bacteria are allowed to proliferate within there, and those bacteria are what generate hydrogen sulfide. And turns out they're also the home to the methane formers. So if you're going to treat for H2S, you're also likely going to be treating for methane. So keep this in mind when you're looking at projects for odor control, where you might also be able to receive credit for methane reduction by doing the exact same projects. I'm going to show you a little bit more evidence about how much methane is actually formed when it comes to all wastewater treatment. So greenhouse gas estimation protocols historically have assumed that there is no methane formed in sewer pipelines. However, the research here by Brown and Caldwell and WEF suggests that over half of the US centralized wastewater emissions are in fact from the sewer. So if half of all wastewater emissions are in the sewer, it does make sense to investigate how to reduce those emissions in the sewer itself. Now, a little bit about the methodology that Brown and Caldwell used to develop some really easy equations that we can use in the water sector to determine methane formation. So I'm going to step away just a moment from hydrogen sulfide and focus really on the methane. And this diagram here is a good indicator of how elaborate their models were. So they took into a lot of different, into account many different factors, including, the volume of water in the pipe, the slope, the headspace, the diameter of pipe, a lot of different things. And I'm going to get into very few of these details that are published in this document. So here they have developed a couple of different equations depending on what type of sewer pipeline you're looking at. So if you've got a gravity pipe, like what's pictured up here, there's a headspace of air, which makes sense that this would uptake some of that oxygen and produce slightly less methane than, for example, a full sewer pipe, what they call surcharged, or a force main. So when this force main is full of water and has no headspace, the dissolved oxygen is rapidly consumed. So those anaerobic conditions persist, and the H2S and methane are then formed. So you've got a different equation, whether it's a force main or a gravity main. And those two equations are summarized down here. So with the gravity model, you can see that this R is the methane emissions rate per kilometer per day. So you plug in some different variables for temperature, flow, pipe diameter, and slope, and you can really easily estimate how much methane is going to be formed in this section of gravity pipe. And it's even easier for a force main. So there's only two variables here, really. It's the diameter and the temperature. And that can help you estimate what the methane formation in a sewer force main would be per kilometer per day. I'll give you a few examples. But first, just to show you why this equation is so simple, just take a quick look again. R is 3.452 times diameter of the pipe, and temperature is in there. So you can see that flow really has no effect on methane production. It's a flat line. Also, COD and sulfate have very little effect on methane formation. However, the pipe size is a linear relationship, and temperature is also a factor. So this slide shows that equation again, and you can see a few more variables this time because we're showing the equation for if it's not a constant flow force main, if you've got a pump station that's on a fill draw. So there you can incorporate those number of pumping events in the pumping interval. But the equation, much simplified for continuous flow force main, is also proven with real life testing results. So you can see in this data plot here, the real life analysis falls very, very close to this equation right here. So it's a very accurate equation. Now, when we talk about methane and greenhouse gases, you may not be as familiar with the methane as you are with carbon dioxide. So we'll talk a little bit more about how to relate those two. Methane, CH4, is 30 times more harmful than carbon dioxide, CO2. We said that earlier. But just to kind of consider, 1 pound of methane is kind of equivalent to 30 pounds of carbon dioxide. And just to give you a baseline idea in terms of cars, one car produces 33 pounds of carbon dioxide a day. So you can kind of consider that 1 pound of methane is kind of like one car. So we'll use these examples going forward to understand how this may relate to your collection system. So I've taken some data from a couple of projects that we've worked on where I have a lot of information on the length and diameter and different things. And I've got two examples here using this equation. And these were both systems that were at 25 degrees Celsius. And so 1 mile of 18-inch sewer force main can produce 7.5 pounds per day of methane. That's like 82,000 pounds per year of carbon dioxide, or like driving 7 cars all year long. So if you treat that force main appropriately, then it's like pulling 7 cars off the road for each 1 mile of 18-inch force main. Think of how many miles of force main are in your utility department. Another example here is 1 mile of 24-inch force main. Running the numbers through, this can produce 10.8 pounds per day of methane. That's equivalent to 118,000 pounds per year of carbon dioxide, or 10 cars being pulled off the road if you treated that 1 mile of force main. Now, when we talk about different ways to reduce that or to treat that force main so that we do not have the anaerobic conditions, We do not produce the hydrogen sulfide, and luckily, we do not produce the methane. So good ways to treat and reduce these harmful gases is really the best way is to inject pure dissolved oxygen, because this is directly combating those anaerobic conditions. Also, nitrates can have a very similar reaction. Iron salts can have an impact on sulfide control as well as methane formation. So this graph here by Brown and Caldwell shows that the addition of ferrous and ferric iron for sulfide control was also found to impact methane formation rates. However, it does not completely preclude that from happening, like dissolved oxygen does. So if you're to work toward methane reduction by using pure oxygen or a nitrate, you're not only doing the right thing by reducing greenhouse gases and doing your part for climate change, but you're also going to be able to claim these other benefits and other reasons to act now. It's to also protect infrastructure. So when you reduce methane, you're also reducing H2S. And when you reduce H2S, you're protecting from that corrosion. And you're also going to be reducing costs from preventing those failures and repairs down the line to the pipeline. You can also stop the odors and improve air quality. Also, locally sourced oxygen has a smaller carbon footprint than purchasing chemicals that are produced maybe on the other side of the country. Also, pure oxygen has no harmful byproducts. So there are many different reasons to act, not just to go for strictly methane reduction, but it can be an additional benefit to something that you're already focused on. So I'm going to show you a case study or an example of an oxygenation project that we did and was presented by Dave Kleidens at the WEF Air and Odor Conference in 2018. And this is a system that was installed in Raymore, Missouri, which is very close to Kansas City, home of the Chiefs, go Chiefs. And this city was noticing that they had some force main leaks. And so they hired a firm to come in and investigate, and they found some pretty bad corrosion. They also had a lot of odor complaints, and between the odors and the corrosion and replacing 4,000 feet of pipe, they decided that they needed to do something different to make sure that this doesn't happen again. And I'm going to show you what that looks like. So this force main is 17,000 feet long, and it's 24 inches in diameter. And the water takes a little over 13 hours maximum to get from point A to point B. Now, for such a long residence time in that pipe, there was a lot of H2S formation. And by stopping, or what they decided to do was to add dissolved oxygen in order to stop that hydrogen sulfide formation. And as we now know, they were also stopping methane formation. But we've got the information here on hydrogen sulfide because that was their main objective at the time. So we've got an odor logger showing each day is a mark on this x-axis. So this is October 21st, October 22nd, October 23rd. And this is untreated hydrogen sulfide levels at the end of that force main, 3 miles long. And each day you can see it was at it spiked up to about 800 parts per million with a weekly spike of almost 1,000. And this is extremely high levels for hydrogen sulfide. It's very, very unsafe. Also, it encourages extremely rapid corrosion. H2S only needs to be at a level of only like 20 parts per million to establish near maximal corrosion rates. So think of the corrosion rate at a level of 800 parts per million in the gas phase. Now, when they turned on the oxygen feed, you can see here that the level of H2S flattened out immediately below 1 part per million. So they're stopping odors, they're stopping corrosion, and they're also reducing methane. So they're meeting these multiple objectives. So we talked about cutting down the H2S, but for this specific project, let's talk about how much methane was also reduced. So this one section of 3 miles of 24-inch force main, has the potential to produce 24.3 pounds per day of methane, or 4.4 tons per year. That's the carbon dioxide equivalent of 24 tons per year. The car equivalency is, it's like 22 cars driving nonstop. So by treating for hydrogen sulfide, it's like they're taking 22 cars off the road. This is a photograph of what that system looks like. They're outside of Kansas City. And here is the analysis table put together by Ken Newport of HDR, who designed this project and did the analysis. And he wanted, before he decided on oxygen as the best option, they looked at many other chemicals, all the alternatives that were available for slowing or stopping hydrogen sulfide, odor, and corrosion. And you can see these were all over $100,000 a year to operate, which in contrast, the oxygen system with ECO2, with the power and the oxygen feed and everything, is only $30,000 a year to operate. Just for a little frame of reference, they're feeding just under 1,000 pounds per day of oxygen, and they're targeting 180 milligrams per liter of DO. They have a high pressure force main, so they can get a lot of oxygen dissolved there to last throughout the entire force main. So above the cheapest chemical, we're saving $123,000 a year. Now that total project was about $650,000 with the capital and the installation all included. And they're saving $120,000 a year on chemical savings. So over a 20-year payback, they're saving up $1.8 million over chemicals over 20 years. Plus, they're stopping corrosion, they've stopped the odor complaints, and they're reducing the methane. Now, just a quick step back to take a look at what ECO2 has done in our 21-year history of sewer pipeline projects and what we have done to combat the climate crisis. For all of the projects that we have currently operating in wastewater pipelines, we're feeding 19 million pounds per year of pure oxygen. And by doing that, we're saving our clients from feeding 5.5 million gallons per year of a nitrate-based chemical. And in doing that, for 21 years, all of our projects, we've removed 3.9 million pounds of methane, which is equivalent to 80 million pounds of carbon dioxide over those years, and equivalent to taking 1,000 cars off the road. So I'd like to turn it back over to you and ask you, where can you make a difference? And where can dissolved oxygen help you make that difference? Here's my contact information. We've got some other support information available for download. If you'd like to receive any of that, or if you'd like to receive a certificate of completion for a half hour for this webcast session for continuing education units, please email me at atrollier@eco2tech.com, or my phone number is there. Contact us anytime, and thanks for tuning in.